Hello and good day. With this video, I will describe to you how we've used the Jupyter notebook to create a model that detects and alerts anomalous traffic going into a network. So we named this the machine learning project for our group 14. First step we did was to import libraries, tools, and data sets, as you can see. So we imported several libraries. I will just run the codes as I go along. Imported pandas, seaborn, numpy. These are some of the libraries we will use as we go along. Next, we had to load and view the training data sets, training and testing data set. Now we're using the UNSW15 data set for this project. This data set has training part and it has a testing part. They are both CSV files, and we imported them from Cargo, downloaded them from Cargo, and we already have them on this local system, this local machine. So the next code you will find is we created objects to read using Panda these CSV files for the training data set and the testing data set. So we named the training data set train, the train object, and the testing data set test. So I'm going to run this. So to have an idea what the train data set looks like, I'll print it. I'll run this code to print just the head, the first 4 columns. So this gives an idea of what the data frame, the train data frame looks like. It has 82,332 rows and 45 columns. You can see all the columns or attributes here. If I scroll down, you can see here that it has attack category column, which is our output column. Now, it has a label column as well. The label column is binary, having only 0 and 1. So 0 for the normal traffic and 1 for the attack category traffic, despite what category it is. Now, I can also run a tail to see the tail of it. The tail of the data, the train data set, the last 5 columns, the last 5 rows, sorry, and you can see as well. Now, with this, we have to try and understand the data set. So we performed some exploratory data analysis on the data set. So I'm going to run this to understand the data set. So first thing we did was to try and understand information. So we're using this train.info to understand what the train data set is like. This displays an output for us. It gives us all the attributes of the train data set. You can see there are 44 attributes. It also tells us about the type of data type of each attribute and the count type as well. So it has no null values, and some floats and others are integers as well. So this was just data exploration, data analysis, exploratory, trying to understand the data. We also run another code here to describe the data, the mean, count, and just better understanding the data. We did some visualizations as well. So scroll down there. So for visualizations, we try to use the count plot from seaborn library to understand what the frequency occurrence of each of the categories, the attack categories are. So this gives us this figure here. So you see the normal traffic has the highest, and then you have all these other ones are the kind of attacks and the frequency. We used the count plot from seaborn libraries for this. We had already imported seaborn as SNS, and then we use the count plot, putting the x-axis as our target and the our data from the trained data sets. So went further to try and understand the spread of these different attack categories with respect to specific or selected input variables. So the first input variable we're trying to see the spread with is rate. So we want to see the spread of the normal traffic has a high spread, backdoor reconnaissance. So the attack category with the least spread on with respect to rate is worms. We did this with respect to others as well. So you can see if I keep running around these as well. That's with respect to S bytes. Run with respect to trans depth. You can see these do not have very high spread. The output doesn't have high spread. Then with respect to the duration, the spread is better with the spread of our attack categories is better, and we use the violin plot for this, the violin plot 2 from Seaborn library. So the last visualization we did was a relationship visualization, trying to see the relationship between our attack category and our selected input variables. If I run that, this will bring out this relationship plots, which we also imported from Seaborn library, and you can see the normal traffic had the best relationship with our S load input variable, and the other attacks, as you can see here, have varying relationships. We can see here that the analysis and worms also have very little relationship. So we did this with other input variables as well, with DLoss, as well as with SMean, and then it gives us different results. So you can see we had a better understanding of the spread and relationship and occurrences of our output data. Now, with this in mind, we proceeded to begin the pre-processing of our data sets. Now, first we checked for missing values using this train.isNull method.sum method, and good thing there were no missing values in all of our data sets. Every column had values, every row, every cell had values. Next, we tried to see the data types. So we ran this train.data types. You notice we have been working mainly with the train data sets because the train data set is what we use to create the model, and it is also the same. It has the same features as the test data set. So instead of working with both, now we saw from this that we had 4 objects, some integers, and some float data types. So we wanted to see which ones are actually the objects, which are categorical data, so we know how to convert those to numeric. So we had 4 columns of 4 attributes that are categorical data: proto, service, state, and attack. Proto being prototype. So these 4 columns are object data type, and we need to convert them to numerical data so that they can be able to work with our model. To do that, we use the feature encoding technique, feature engineering rather, using the label encoding technique, and we transform categorical to numeric. We imported a tool, the label encoder, from the sklearn library, and we called it with this object le equals to the label encoder method. We We then run our train data, creating 4 new columns, numeric columns, which we will use to replace the existing categorical columns as we had identified earlier. Both for the train and for the test data sets, we created 4 new numerical columns. Now, we are using the label encoder to create these 4 new columns and fitting it into our existing data frames. So as you can see, so the train data frame, we're adding the proto underscore LE, which is label encoder, and we are fitting it to train dot proto type. So we are saying we are fitting it fit underscore transform. So this actually does that. When we run this code, you will understand what I did when I display the head. Yeah, when I display the column of our train data frame. If I scroll down to the right, you can see these are the 4 new columns created, and they are numerical. The 4 previously existing ones are still there. They are still categorical. We just created 4 new to replace labels, numeric labels to replace the categorical labels. Now, after doing that, we then display this categorical data and corresponding numeric data. So this was the categorical data, and this is the numeric data in the new columns. So I will do this for all 4 of them. This is important, and I will pay particular emphasis to the attack category, which is our output dataset. Now, this would mean, if I run this as well, it will mean that for this is our attack category. It has the normal, traffic, recon, and the others are all attacks, forcers, worms, as the case may be. So we created a new column, train.attack underscore LE is the new column we created. Now, these labels represent the formerly existing categorical or these ones. So where we had normal will take the label 6, and where we had generic take the label 5. Shellcode take the label 8, and this will come up later when we build our model. Now going forward, we have to remove the existing categorical, as we have already replaced them with numeric data, and then we run that. So to remove, we just drop those columns. We drop the existing categorical columns, both in the train and the test data. So we drop them. Next, we remove the ID column, which is actually not adding any value to our model. We take that off as well. And then we can view the first four rows of our data set. You can see that the categorical columns have been removed, and we only have numeric data on our data set now. And then the next thing we do now, we can proceed to assign input and output variables to our data set. Input being what goes into the model, output being what we expect to predict. So for our data sets, our input data is all input attributes are all the other columns except the attack category column, and our output variable is the attack category column. So we assign the x value. We assign the input variables to the x value and the output variables to the y value. Now, so we do that by just using this code here. So we created a new data frame, s underscore train, from the train data frame, and we dropped the attack underscore LE. So this is now our input data frame, while the y is attack underscore LE, which is the output data frame. Now, the next thing we'll do is so we do this for the test as well. We did it for the train, so we'll do it for the test as well. Now, after that, we'll look at the shape of both the test and the train. So this is the number of rows and columns for test and train data set. The last thing we do before we build our model is to feature scale, because the range of our values between our attributes was so wide, the range of the magnitudes. If I go back a little bit, yep, you can see here that while some of them rate has the 90,909, others have just 1, 2. So the magnitude ranges are so the divergence is too large, and we need to keep the ranges scaled so that we have more accurate results from our model. So I'm going to run this, and then I will import. First, we imported the standard scalar tool from the sklearn library, and created this object sc called the standard scalar method, and fit it into the existing x.train and x.test, so we can have a feature scaled. This will give us an array, and you can see now that from the outlook of the array, every column of this array now has attributes and in the same range, unlike the magnitudes that were previously very, very wide apart. So we can then proceed to build our model. Now, to build our model, we use algorithms. So we import the first algorithm. We import the random forest classifier. The random forest classifier we import it from the sklearn library. Then we create this random forest objects, and then we fit our x_train and y_train, that's output and input data. We use them to train this random forest classifier. I'll run that so we can get a model. We train the classifier to give us a model which we can then use to predict. So when we train it, just wait for that to run. We train the classifier using our existing data frames which we had already scaled, the x_train and the y_train. Recall these are from our train data set, not test, from the train data set. So we've created the output, the random forest model. Now we have to test that model. So we test the model. To test the model, we'll go and use the test data set, not the train now. So we'll use the input of the test data set to predict what the output will be when we feed it into our model. So we run this to feed it. So we predict, using our random forest model, we predict the input of the test data set, and it gives us this array as an output. Now we'll have to compare this output array with what the actual output data set is. And when we do that, we can get an evaluation to see, because y_test is the actual output data set. Now we are comparing it with the predicted data set which we got from our tests, and you can see we got precision, recall, F1 score. So it gave us accuracy across board, weighted average, and macro average as well. Now that we have been able to get a prediction, which is like that prediction gives us the different kind of attack categories and also normal traffic based on the model we created. We then, the final step is to alert the administrator of the system when we find in our prediction labels related to attacks. So to do that, um, we have to examine that predicted array. But first, we convert the array back into a list. So I did that with this. So this is the array. We predict underscore random forest array. We use the to list. We converted it into back into a list, and from this list we use if and else if statements to predict, to analyze the prediction. So if the label is equal to 2, depending on what label attacks are, it will return display either of these for the administrator, so the administrator can be alerted of an anomaly in the system. Now if I run this, because our current data set has all the different, which is not true in reality, it cannot have or sometimes may, you find that it displays normal traffic on every line. Every time there's inflow of traffic, it analyzes it based on all the parameters we've given to it. After running it through the model, it gives these as a response. So you can see for this particular traffic, it's a reconnaissance attack. We had so many normal attacks initially, but along the line, there was an anomaly. Falsers came in, denial of service came in, and other attacks. This way, the data administrator or the network administrator can be alerted when the when anomalies are detected, traffic flow anomalies are detected in the system. We are still working on the other, for now, we're still working on the other um, algorithms. We're also going to repeat this process for the other two selected algorithms we have to work with, like k nearest neighbor and the other one. All right, I think so far that is what we have. Thank you very much for listening.